Welcome to The Explainer. Today, we are taking on the ultimate cosmic missing persons case. It's a mystery that has completely baffled the absolute greatest minds in physics for nearly 50 years. I'm talking about the black hole information paradox. We're going to dive into some incredibly cutting-edge research that proposes a really fascinating way to solve this cold case once and for all. So buckle up, because today we are reconstructing the scene of this cosmic crime using nothing but the established everyday rules of quantum mechanics.
Here is our quick roadmap for the explainer today. First, the cosmic information paradox. Second, firewalls and page curves. Third, the quantum toolkit. Fourth, islands as quantum measurements. And finally, number 5, solving the paradox.
Okay, let's jump right into section 1, the cosmic information paradox. I want you to imagine a massive star collapsing and swallowing everything around it, including the unique quantum data that makes up our universe. Now, as Stephen Hawking brilliantly discovered decades ago, black holes aren't actually completely black. They slowly leak what we call Hawking radiation, and eventually, over unimaginable timescales, they just vanish entirely. So this sets up the million-dollar question, right? What happens to all that specific, unique data that fell inside? Where does it go when the black hole is just gone?
While this creates a massive fundamental conflict between our two best rulebooks for how the universe works. On one hand, general relativity tells us that once something crosses the event horizon, it's permanently trapped. So when the black hole evaporates, that information is utterly and permanently destroyed. But on the other hand, a core axiom of quantum mechanics, called unitary evolution, insists that information can literally never be destroyed. It has to be preserved so you can always mathematically rewind the tape of the universe. So we're stuck. If information actually escapes, it breaks our entire understanding of gravity. But if it's lost forever, that fundamentally breaks quantum mechanics.
That brings us to section 2, firewalls and page curves. Now, take a look at this page curve. It tells a really dramatic story about this missing data. It's visually tracking the entanglement entropy of a black hole over its lifespan. See that dashed line going down? That's the black hole's shrinking capacity to hold entropy. And the solid line going up, that represents the entropy of the Hawking radiation leaking out. For a very long time, physicists assumed that solid line just kept going up forever, which would mean the radiation coming out is completely mixed and carries absolutely zero information about what's inside. But if that data is going to be saved to protect quantum mechanics, that solid line absolutely has to eventually turn around and come back down to zero.
And that peak right there in the middle of the graph is what we call the page transition. It marks the exact turning point in a black hole's life. It's the moment when the black hole has radiated away enough mass that, to preserve those crucial quantum rules, the outgoing radiation actually has to start becoming purified. The entropy has to decrease, and the data must start coming out. But for years, physicists were totally stuck on this. Figuring out exactly how that data gets out without creating a catastrophic, fiery wall of energy at the event horizon, what they call a firewall, seemed absolutely impossible.
Let's move on to section 3, the quantum toolkit.
To solve this paradox, without relying on those destructive firewalls, we need to take a quick detour. We're going to step away from massive, galaxy-sized black holes and zoom way, way down into a microscopic quantum laboratory. We need a specific toolkit here, one containing quantum teleportation and entanglement swapping. Now, I know that sounds like science fiction, but these are real, highly verified protocols used in labs today. Here's how it works. Step 1, you share a highly entangled quantum state between two different locations. Step 2, you perform a specific type of joint observation, called a Bell state measurement, on one end. And Step 3 is where the magic happens. The information of a separate independent qubit transfers to the other location instantly. It doesn't physically travel through the space in between. It's a total state transfer driven completely by entanglement and measurement. And this mechanism, the skipping the space in between, is exactly the trick we need for our black hole.
This brings up the famous Alice and Bob scenario you see right here. As we know from the quantum no-cloning theorem, you absolutely cannot make a perfect copy of a quantum state. So if Alice falls into the black hole holding a secret quantum message, and the black hole somehow also radiates that exact same message out to Bob on the outside, well, we have an illegal clone. To avoid this cloning problem, physicists previously argued there just had to be a firewall that aggressively burns up all incoming information right at the horizon. But what if we could use our new quantum toolkit? What if we could teleport the information out without cloning it, and without burning poor Alice to a crisp?
All right, section 4, islands as quantum measurements.
So now we take our shiny new lab tools and apply them directly to the black hole itself. The crucial point of this entire breakthrough is this dictionary right here.
The researchers have perfectly translated terrifying abstract theoretical physics jargon into approachable quantum information concepts. Look at this. An entanglement island, which is a region inside the black hole physicists use to calculate entropy, translates directly to our Bell state measurement. A replica wormhole is just our teleportation protocol. The scrambling time? That's simply the time it takes to complete the measurement. And that page transition we looked at on the graph earlier, it's simply the quantum to classical transition point where these measurements effectively kick in.
I really want to pause and emphasize this, because it's a massive breakthrough. An entanglement island inside a black hole isn't just a physical location or some weird mathematical anomaly. From the perspective of an observer on the outside, this island acts as a literal quantum measurement device. It operates as a projection operator. When quantum information hits it, the island itself triggers the exact same teleportation protocol we just learned about in the lab.
And that brings us to Section 5, Solving the Paradox.
Okay, let's walk through this and anchor all that abstract math to what's actually happening here. See that slanted red dashed line? That represents our entanglement island. Right at the event horizon, a pair of Hawking particles is created. One of them falls in, that's arrow A, and one escapes, that's arrow B. Now, arrow D over there is the early radiation that left the black hole ages ago, and it's still entangled with the black hole's internal state, which is C. The key moment is when that infalling particle A finally reaches the island and gets measured against the black hole's state.
So how does this actually play out to solve the paradox? Because the island acts as a projection measurement, it effectively triggers an entanglement swapping protocol on a massive cosmic scale. The infalling particle A annihilates with the black hole state C. And because of that pre-existing shared entanglement we talked about, the data inside the black hole instantly teleports to the outgoing radiation. The early radiation is successfully purified, and that page curve we saw earlier, it safely turns around and comes back down to zero. The ultimate aha moment here is that because this data rescue happens dynamically via teleportation, literally bypassing the physical space, you never actually need a firewall. The event horizon remains completely smooth, nothing burns up, and the rules of gravity stay perfectly intact.
Now, I will absolutely acknowledge that the underlying mechanics of this are incredibly complex. Just look at this circuit diagram mapping out the sequence mathematically. Time flows upward here. You've got your initial states at the bottom. They pass through a scrambling unitary evolution, that's the box labeled U, and then they hit those curved loops at the top. Those loops represent the Bell state projections happening at the island. The right side of the diagram shows you the mathematical equivalent. The data successfully ends up on the outside, totally preserving the unbreakable unitary rules of quantum mechanics.
To translate that intense circuit diagram back into plain English, the source research sums it up beautifully. The island simply acts as a gateway. It is the mouth of a replica wormhole, which, remember our new dictionary, just means a teleportation protocol. Information entering the island goes through this protocol and safely returns to the asymptotic region, which is just a fancy way of saying the safe, distant universe outside the black hole. The cold case is finally closed, and we did it just by trusting the deep, fundamental rules of quantum information.
But before we wrap up, the researchers leave us with one absolutely mind-blowing realization. In order for all of this to work, we have to accept that a black hole acts as an objective measurement device. It forces a quantum wave function to collapse naturally on its own. And this leads to a massive question. If black holes can spontaneously measure and collapse quantum states out in space, could understanding them be the key to solving the fundamental measurement problem of quantum mechanics right here in our own Earth-bound laboratories? It really seems like the deepest, most confusing mysteries of the cosmos might actually be the key to understanding the building blocks of our very own reality. Thank you so much for joining me on this explainer, and keep questioning the universe.